Hello, welcome to the Big Bang. My name is Capelina, and today we'll be talking about the sliding filament theory and how it relates to the muscle length tension relationship. Let's begin by going over the basics of a sarcomere before we dive into the sliding filament theory. Sarcomeres are the building blocks of muscles. They help the muscle to contract. A sarcomere is made out of two main proteins, actin and myosin. Actin filaments are thin filaments and are attached to Z lines, which are lines that mark the boundary of a sarcomere. Myosin are thick filaments that overlap with actin at the M line, which is in the middle of the sarcomere. Actin and myosin slide past each other, and the myosin attaches to the actin in order to form a cross bridge. Those cross bridges are what ultimately makes up a contraction. The myosin then pulls on the actin towards the M line, which shortens the sarcomere. In an active force length curve, as more cross bridges are formed, the more force is generated in the sarcomere. The amount of force depends on the length of the sarcomere. During the ascending phase, the sarcomere is in a shortened phase, meaning that the sarcomere is too short to make cross bridges. So the force generated starts low and increases as more cross bridges are formed. At the beginning of the plateau phase, the length of the sarcomere is at the optimal length to form the most number of cross bridges, so the sarcomere produces a maximum force. During the descending phase, the sarcomere stretches, so the active filaments are out of range to form cross bridges, so the active force decreases significantly. In a passive force length curve, the protein titin is responsible for passive elasticity. Fun fact, titin is a gigantic structural protein, being considered the largest in the human body. When titin is coiled, the sarcomere is short and generates less force. However, when the titin stretches out, the sarcomere gets longer and generates more passive force. This structural protein, titin, is responsible for developing passive stretch, which is when the muscle is being latent in a passive state. For example, you feel a passive stretch when you try to touch your toes. The active and passive curves can be combined in a total force and represented in a muscle length tension curve diagram. The blue line represents the active force, meanwhile the orange line represents the increase in passive tension as the active tension decreases. The green line represents the overall changes in the force in the muscle. Those cross bridges that we discussed in the beginning are what contributes to muscle contractions. There are three types of muscle contractions: concentric, eccentric, and isometric. For concentric contractions, the muscle shortens during an active contraction. In this scenario, the muscle is lifting an external load that is smaller than the maximum force being produced by the muscle. One example is lifting a weight during a bicep curl. The next type of muscle contraction is eccentric. During an eccentric contraction, the external load or the force applied onto the muscle is greater than the maximum muscle force being produced. As a result, the muscle lengthens due to the high load. One example is lowering a bicep curl. The last type of contraction is isometric, where the muscle is contracting or generating force at a constant length. One example is carrying an object in front of you. Next time, we'll be covering the force-velocity relationships in muscles. I hope that this video was helpful, and thank you for joining us. I will see you next time.